Okay, so first of all, congratulations to making it through the whole conference to the last session. And thank you for choosing my session. So honestly, I would also be having really hard time choosing because all of them in this time slot were super interesting. So thanks a lot for coming here. I hope you will not regret it. And yeah, so this session is going to be about AI. But let's make it a little bit more interesting and don't talk about LLMs, but let's focus on something different. So I would like to talk about something called continual learning. So the ability of the machine learning models to learn continuously. And I would like to tell you this story in 3.5 acts. And during this time, we are gonna explore what continual learning is, when to use it, and we're also going to see how it helped us to solve one of the issues we were having in the healthcare-related area. But as this is my first NDC and my first time in Australia, I would like to introduce myself. So my name is Agata Chudzin ska. As you can maybe hear from my last name, I'm Polish, and this is how we're sometimes laughing that this is the way how we smile in Poland. So just very slightly, especially when you're on the streets. So yeah, but I'm working for a German company where I'm CTO and AI solutions architect, and where we are building customized AI solutions. And I have been working on the implementation of different AI and machine learning models, especially in the areas of natural language processing and computer vision for over the last 8 years now. But we did that for many different companies from various industries. But what would be quite relevant for this talk is that we have also worked a lot with companies from the medtech field, so more healthcare-related projects. But what does it mean? So we have mainly worked with processing of medical images, be it detecting different and segmenting different anatomical structures on medical images, such as bones, here a bit more complicated liver, but together with all of the different tiny veins that are in the liver, which are super crucial for the liver resection. And also implementing it in extended reality applications that the surgeons can use for the planning or for the patient education, be it on a Microsoft HoloLens when there is still supported, or Apple Vision Pro or Meta Quest right now. But I would like to focus on one of our most challenging projects in this area, which were connected with so-called focal cortical dysplasias. But before we dive deeper into that, I would like to bring to your attention some statistics that were quite shocking for me before I started working in this area, which are that more than 50 million people worldwide have epilepsy, and according to some statistic, even 1% of the global population, which is really a lot, and which is making it one of the most common neurological diseases globally. And if having epileptic seizure is not itself enough, every epileptic patient is 24 times more likely to die unexpectedly because of the phenomenon called sudden unexpected death in epilepsy patients, in short, SUDEP. So I think you can agree with me that this is quite a serious problem, and detecting them is really crucial to make the lives of these people easier and better. So if we would like to dive a little bit deeper into epilepsy, sooner or later we'll come to something called focal cortical dysplasias, or FCDs. And in short, they look like that. So what are FCDs? If we take a magnifying glass, they will look like this. So they are some errors, some misbuildings in the brain development, which have very high epileptogenic potential, meaning that they are very frequent cause of epilepsies. And they are responsible for above 70% of the drug-resistant epilepsies. So not all of the patients can just take some drugs and then live a normal life. And for a majority of them, these are the FCDs who are the reason for that. The good news here is that they are potentially operable, but the most important thing is to find them. So let's analyze how do they look like on MRIs, because that's the way how we can find them. And if you're above 30, you probably already had some MRIs in your life, but if you're lucky enough and you didn't, so very short intro. So basically, MRIs stand for magnetic resonance imaging, and this is a machine learning magnetic MRI scanner. So this is basically a tube, you go into that, it's making some weird noises, quite loud, and is making a series of pictures of your inner body using magnets and radio frequencies. So let's come back to our FCDs. So we use the scans from MRI scanners to check if the FCDs are there. So there are some features that can be present in the same time or in some combinations, so this is not like exclusive list, but these are the most common features that we can see. So first of them, one of the most characteristic ones is blurring between the boundary of the white and gray matter. Later, there is also some thickening of the cortex, as well as some unusual duration of the brain, some foldings that are quite unusual, as well as the hyperintensities of the white or gray matter, some brighter spots that we can see, and quite characteristic transmantle sign. So this is a form of a visible path towards the ventricle that you can see here. And also, which is making it the task not easier, FCDs can vary in shape, in location, and they can also blend into the surrounding tissues. But when things go well, and the FCD is being detected mainly by epileptologists, the patients can undergo brain surgery and become seizure-free and live a normal life. So the stakes are very high, so having all of that knowledge that you already have about FCDs, I have a task for you now. So we are going to see 3 pictures of 3 MRIs. And your task is to tell me if there is any FCD present in any of these. So we will have a few seconds. Any ideas? It was a bit tricky because all of them have. But as you can see in what's typical, it's not like in the books that you have all of the very typical features being there that you can recognize it. I mean, we have worked for this project over a few years, and even though we have seen like really lots of them, we wouldn't be able to do it. Like, it means that you really, really need an experienced epileptologist to recognize them. And as you can imagine, having this kind of niche knowledge is very rare, which leads to the fact that the majority of these patients never get proper diagnosis. So we came to the idea, how about using AI to detecting it? I mean, there are some subtle patterns in this data that are hard to detect maybe for a human eye, but they still exist. This is very niche knowledge, and democratizing it would really help in many cases. So we thought, yeah, that sounds really perfectly like machine learning. So we have taken our team as AI experts. We cooperated with the biggest epilepsy center in Germany, which is in Hamburg. And we even have taken real Dr. House to make our chances even higher to succeed. So we started with the data sets. As you may know, in machine learning, data is king. Like, you really need to have good data sets to achieve good machine learning models. So we managed to collect the biggest to this point data sets consisting of over 200 magnetic resonance imaging series, so each of them almost 200 images, with FCDs, which was the biggest to this point data sets collected globally. Like, no one was ever before writing about having a biggest data set with them. But we didn't want to just recognize, okay, here is the FCD, knowing that it should be somewhere in this series. So we wanted to make it useful for the daily clinical practice. So that's why we have also taken 100 normal MRIs, as well as 50 MRIs with different pathologies, like not healthy brains, but including some different pathologies in there. We have taken the T1 and FLAIR sequences, so this MRI machine, this can have different settings, and then you can expose some different features. And most common ones are T1, T2, and FLAIR, so we decided to take 2 of them. And what's important, we have also taken all of the MRIs, like even with the suboptimal quality, because that's what happens in real life. And when it comes to the ground truth, as you have seen, this is quite tricky to recognize them. So we really used lots of different methods to really be sure that these FCDs really are FCDs and exactly in these places. So these were a few epileptologists checking them, as well as we're checking the type of the seizures and the EEG data to be sure. One important part why there weren't so many data sets like that before is also the way how you collect this data, meaning that you really need to have a lot of knowledge, but also a lot of time to prepare the data set and to manually adapt them and to manually create the masks, as you can see here on this picture. So we have our data sets, so let's go to training our neural network, right? Well, not so easy. I mean, I would have lied if I said we didn't try to do that, but it turns out that having such complicated and subtle patterns in the data, you either need really a lot of this data, which is not so easy to get, or you need to use a bit different tricks. So we have on the second way, and we have also included some pre-processing of the data. So we have done this in 3 different steps. So first of all, we have decided to do the brain tissue segmentation. So we did that using, this is quite easy problem. You can easily achieve around 95% of accuracy with existing models, so that was nothing novel. And we did that for skull stripping, so that we removed all of the unnecessary data. But we also did that so that it was the prerequisite to the second step. So it turns out that epileptologists are also using some different techniques to make their life a little bit easier. And one of them is the morphometric analysis. So these are kind of the filters that you can apply to the pictures so that you can expose some of the feature more. And we use 2 of them. So first of them is called junction. So it needs to have the gray and white matter masks so that you can calculate the intensities and standard deviation and mean of them, so that you can expose on this on the first picture the features here. Another one quite interesting is the extension, meaning that if you apply some additional blur to something that was already blurry, it's also exposing it. So I also lately got to know that this is also a trick used in cybersecurity. So if you also apply some additional blurring, you can see which parts of the picture have been adapted, for example, in Photoshop, etc. And finally, we have used the 4 channels, so the T1 flare, our 2 additional masks, as well as we have done some standard padding, cropping, and preparation of the data. So this is the part where we could go to our neural network architecture. So we have really checked a lot of them. We also tried the transfer learning approach, meaning that if we already were doing a lot of the segmentation, so we decided to try to take this and slightly adapt. Well, that didn't work, so we needed to start from scratch. And this is a short version of our architecture. So each of these blocks has its, again, different layers. If you're interested, I will also reference it at the end. But in very short, we used a bit the architecture called UNet and adapted it a bit to our needs. So this is quite common in the medical segmentation process, which in short relies here on the idea that we are using encoder-decoder, meaning that we encode first the information from our original image so that we create a bottleneck. And this bottleneck is much, much smaller, but it encodes a lot of features, so it has quite depth when it comes to recognizing features such as edges, shapes, etc. And in the next step, we take this bottleneck and we try to recreate it again so that we get our features so that we get either the original picture or the segmentation mask, which in this case is quite large FCD. And to this, we also applied additional variational decoder, so it just allowed us not to overfit. so that the model doesn't learn by heart the examples that we're having in our data set. So let's take a look at the metrics and the results that we got. So talking about metrics, we use the classic ones like precision and recall, just to see how many times we're right, how many times did we say wrongly that there is an FCD. But very importantly for the medical field was also explainability. So we used the dice coefficients to do that and to measure the voxel-wise metrics. So as we have pixels in 2D, in 3D we have voxels. So these were the results that we got. I will highlight the relevant part for us. So by the way, it turns out that the more normal MRIs we used in the training, the better it was for the model. And we achieved actually quite nice metrics here. So we are in about 70% of the cases right. Then we're 54%, like this is the metrics saying that we didn't say that many times wrongly that something happened. The dice coefficient is always a bit lower because achieving pixel or voxel level precision is very, very hard even for the annotators to prepare the data. So we are quite happy with our results, and we decided that we'll do the clinical study because you usually do that before you start using it in a medical practice. Meaning that we have taken all of the patients that were in the epilepsy center, and apart from having the normal standard diagnosis that there was, we also checked them with our model. And these are the results. I will again highlight the relevant pieces. So let's take a look here at the first row. And when it comes to the columns, the first one means that we're the neuroradiologists, so the people who are specialized in analyzing the brain, but not necessarily only in epilepsy, like in case of the epileptologists, but in general also different pathologies. So they were able to recognize just 3 of the FCDs that were present there. In the middle, we see the grand truth, meaning that in reality there were 9. And the right-hand side column is showing the results of our model. So we were able to recognize 7, which is really great, better than many experts. So we were quite happy about it, but until we also saw the next feature that is presented here, meaning that we recognize almost 80% of the cases right, but the specificity was very low, meaning that our model very frequently was saying that there is some kind of FCD, where in reality there wasn't. So we decided to analyze it a little bit deeper and see what happened here. So first of our remarks was that for the majority of the false positive cases, our model was saying that there are at least 2 or 3 different FCDs in one example. Whereas when it said there is only 1, in majority of the cases it was right. We couldn't exclude that because that's possible. You still can have 2 or 3 FCDs, but that's very, very rare. Why did that happen? So we also analyzed one by one all of the examples, and we saw that the model reacted quite a lot to the image noise that was there, any moving of the head during making the MRI. It also reacted, for example, to blurring. So it was one of our features, but not every blurring means that there is an FCD present. And we also saw that there was some uneven location spread of the FCDs, meaning that it was quite frequently saying that it is in the frontal part of the brain. So let's sum up the first part with the challenges that we were having. So we are having quite many false positives, which is making it maybe useful for the epileptologists because they already see the areas that could help them, but not really for any other doctors. We collected all of the data in just one hospital, which is the epilepsy center, meaning that there is quite low variance of the data. So if we went to any other hospital and used this model, it might not work that well because this data can be a bit different. Quite obvious, but very important for the second part of the presentation, we are working here with medical data, meaning that they are very sensitive and they are really strict requirements regarding the medical certification regulations. So when we were wondering about what to do next, we also got interested quite a lot at something called continual learning, which was getting more and more popular. But before we dive into that, let's make a quick recap about what do typical machine learning tasks look like in a simplified way. So we start with understanding the problem. Then we collect the data set, we annotate it, split it into training, test data sets, etc. We train the models, so we choose many different architectures, we train them, we got some of the results that look good to us, we optimize them, and we deploy the model, meaning we expose it via API or make it available for the consumers in any other way. So with that, we are happy, our model is working, and we live happily ever after. Do we? Well, it turns out in real life that it is this way, but for some time. After some time, we have some additional things that start to happen. For example, the distribution of the data is changing. Let's say, think of, for example, fraud detection. If you have a really good model detecting the frauds in finance, well, the people are going to change the kind of attacks so that they can trick you. If you're making recommendations to the people, their preferences will also change in time. So your old model will also not be able to catch it that well. So in our case, you might want to see, for example, we said that there are different pathologies in the brain. So why are we detecting just FCDs and not having additional class for the other ones? We might want to have a new task, meaning, for example, we have a good classifier for the documents, but we would also like to have summarizer, which we have a model which already has a lot of skills in this area, why not? No matter how long you collect your data, there will be always some bias in them. So we will also want to catch that in the future. And all of them, in general, influence the decreasing performance of our models. So what we can do in these areas? So let's analyze a few possibilities that we have. So first of them is transfer learning. So let's take a toy example to see what that is. So let's say you have two pets, cat and a dog, and you would like to have a model that will classify the pictures so that you can quite easily take a look at them when you're feeling sad or whatever. So you train a neural network, and it works really great. But at some points, you have a moment of weakness, and you buy a guinea pig. And it turns out right now you have a really nice model that allows you to classify your cats and dogs, but the model has no idea about guinea pigs. So you're a bit sad about that, and you decide you will retrain your model. So you'll just take the model that you have, you feed it with the data with the pictures of your guinea pig, because the model itself already knows quite a lot about what an animal is, right? So we're doing the transfer learning, meaning you reuse the knowledge of the model and you just train it further with the next task. And this is what happens. So while you are training your first task, which is classifying cats and dogs, it very quickly reaches a level that is really great at doing this task. And meanwhile, it doesn't know anything about guinea pigs. And when you start the second task, meaning training with your pictures of the next pet, you get really decent guinea pig classifier, but it also forgets what cats and dogs were. And it's happening quite disruptively. And this is something which is called catastrophic forgetting, and this will be the central point around continual learning, and this is the problem with which continual learning is trying to fight. So another option that we have, instead of using transfer learning, we can just take all of our data, because we just annotated them not so far ago, and train a new model from scratch. Is it going to do the job right? Yes, it does. And this is actually the best solution for this case. But if we think about the issues that we have connected with FCDs, so if we were trying to train the model each time from scratch, we'll have some issues, such as we need to keep all of the data all of the time. So there are some privacy concerns. We cannot forever keep the medical data of some people without stating for how long time exactly and why. Another thing is that maybe our PET classifier is fine with that, but if we are thinking about much bigger models, then we have some significant cost of computation of storage, and also connected with that carbon footprint of the GPU trainings that is getting more and more relevant. So continual learning, or also called incremental or lifelong learning, is trying to exactly address these issues. So the main idea behind continual learning is that the models should be able to incrementally learn and to adapt to ever-changing conditions, and meanwhile don't forget anything what they learned before. And by doing that, they should also be able to reuse what they have learned before, so use their knowledge that they already had, just like humans do. So that's why continual learning methods are also quite a lot inspired by biology, which we're also going to explore in a minute, and the way how the human brain works. And to sum on that, it's also quite relevant that continual learning from experience is actually considered one of the key aspects of intelligence. So if you prefer to look at on a graph, we also have an example here. So the traditional approach, we can also say it's the stateless retraining, which we have on the top part here, like we always train a new model. And in case of continual learning, the idea is that we have a stateful training, and we use just this new piece of data that we're having without touching the previous data at all. So there are three main methods that we have in continual learning. First of them is the regularization-based one. So the main idea here is that we try to penalize the model in the moment when it tries to touch the weights of the neural network that was responsible for the previous task. So we do it via adding additional regularization term to the loss function of our neural network, or in general, we adapt the loss function here. And we adapted based on the parameters that were important, so we weighted by that. And there are also the methods in which we can actually explore which of the weights were relevant for the previous task, so that we can compute it, for example, via Fisher information metrics. Very interesting fact here is that it was inspired by biology, and to be more precise, by a synaptic consolidation. So at some of the experiments, the scientists has discovered that while mice were learning new skills, they were creating new synapses, so new connections between the neurons. And when a new skill was learned by the mice, the connection was getting stronger and stronger, and was getting less plastic, meaning that it was the brain was protecting this connection so that it's not used for any other new connections. And in the moment when this connection was broken, mice were forgetting this skill. So this is exactly the same idea which is here regarding the regularization-based approaches. This method is, although not one to use them whenever, so the issue here is that the forgetting is not fully eliminated, and it's helping us mainly in the areas where this new task is very similar to what we had before, meaning that it works very well, for example, when we have other distribution of the data. Another group of methods are the memory-based methods. So the main idea here is that we store some part of the data in memory, and we use it in the training of the new tasks. So it's also inspired by neuroscience, and quite interestingly by the mechanism of sleep. So while we are sleeping, our brain is repeating some neural activity so that we can consolidate our memories. And this is why the role of the sleep is also so important, especially for children, so that they can build the new connections in the brain. The issue here is that we cannot keep all of the data in the memory because we still have some limitations of the buffer. And if you think about it, it still doesn't help with the data privacy, right? Because we still need to keep this data in memory. So it's not perfect, but there is quite interesting subcategory of this that is very popular in the last month, which is using generative models to create the synthetic data. So instead of keeping original data, we're creating synthetic ones, and we keep these in the memory, which is also working quite well. And the last area here is the architecture-based continual learning, which means that we're adapting the architecture of our models when we are learning the new tasks. So for example, we can do it via dynamic network expansion. so adding new neurons or adding new layers of the neural network, or we can add some specific components. So for example, we can use specific attention heads that are just the last part of the neural network that are specific to separate tasks, whereas the whole model is actually sharing all of the structures as one piece. And the neuroscience inspiration here is by the neurogenesis. So the brain is creating new neurons in the areas, especially in the hippocampus, where it's needed the most, so that they are also being used to create the new skills instead of reusing the neurons that are already used for different tasks. But the assumption here is that we should clearly know what are the boundaries of the task. Like, do I want to right now create a summary or have a classifier? So it still assumes that there is some specific boundaries between them. So having that, let's revisit our FCD case and let's take a look how we combined both of these to solve our problem. So we have decided to use continual learning here, but what we have seen from the clinical validation is that the real data had different distribution, meaning the majority of people, they don't have FCDs, right? We said that 1% of the global population has them, so 99% not. So we adapted the data distribution to mimic better the real life. So for this, we have collected a new data set, but this time FCDs were only 30 here. We use also 150 normal MRIs and 120 with different pathologies. We have divided them into 3 data sets, which we'll use for the different stages of our training. And in each of them, FCDs were responsible for 10% of the cases, 50 normal, 40 other pathologies. As we are using here the different distribution, or maybe you can say that it's actually a new task, because right now we are trying to discriminate better between the FCDs, non-FCDs, and not necessarily detecting exactly where the FCD is. Still, we have decided to use the regularization-based methods, more specifically the elastic waist consolidation. By the way, this is the easiest of them, so whenever you will be trying to experiment yourself, I recommend you to start with this one and then go to the next one if this one is not working that well for you. So let's take a look at our training. So this is our first act, so our baseline model that we used. And for the phase 1, we have just taken the first 100 pictures. So it looks a little bit complicated because it comes from the scientific paper, but let's make it a little bit easier because we needed to come up with some intelligently sounding names, but let's change it. And yeah, so we have taken the first 100 examples, and we have, as the first part, evaluated them against our first evaluation model, which we see here. Next, we have taken it and we have conducted 2 training strategies. So first of them was the classical part. So we have taken all of the data that we were having. From the baseline, we have taken also this one data set, and then we have just retrained the model once again. So we got the first model, let's call it with all data. And meanwhile, we have also second training strategy, which was based on continual learning, meaning that the model saw just this 100 examples. So it didn't see this baseline data set at all. And we trained it and we got another model. Then we have taken the next 100 examples. So we first have taken them to make the comparison. So right now we are comparing against 3 models. So again, this baseline, the model that we trained with all data, and the model with continual learning. We did the evaluation and stored the results. And then we also used the same data to train the next generation of models. Here again, the same strategy. So we have taken all of the models, so the baseline data set, all of the data, sorry. So the baseline 1, dataset 1, dataset 2. So all of them trained the model again, got the new all data 2 model. And in case of continual learning, we have just taken this dataset 2, so meaning just 100 examples. And we also take this model, so the one that was already continuously trained before. It was our starting point. We retrained it and got the continual learning 2. And using the last batch of data, we just could do the evaluation. So we have, again, compared against the baseline, all data 2 and continual learning 2, and did the evaluation, saved the results. So what were the results then? They were very good in our opinion, just to be short. So let's also take a look at them. So baseline did as it did in previously. So no shocking here, sensitivity on the level like 80 or 90, meaning that we recognize 8 or 9 out of 10 example in each of the rounds, but the specificity was very low, still around 5.5, 5.6%. What happened in the model of all data? So again, this was just for the research purposes. Usually we couldn't do that to store whenever we want the data, but we just did it for comparison. So it was able to recognize 8 and 10 out of 10 examples, so it was quite well. And it also increased quite a lot the specificity, meaning that changing the data distribution helped a lot here, that it doesn't create so many false positives. And quite interestingly, what happened with our continual learning, so even though the model didn't have the access to the previous data, it was still able to recognize on the same level of sensitivity, so 8 and 9, here the FCDs, and it increased a lot the specificity. So that was much better than we expected. But we again tried to analyze how did it work this way and analyze each of the cases here. So what we have seen additionally is that for the majority of the cases where our model was still creating the false positives, it was just detecting these different pathologies in the brain. So if we were comparing it only to the normal MRIs, we would have achieved even 90% of the specificity, meaning that it would have really, really great results. And as the training progressed, we have also seen that the model was no longer claiming that the FCDs are always in some specific parts of the model, so changing the distribution also has helped a lot with that. So to draw some conclusions here, we see that using continual learning allowed us to achieve similar level of sensitivity, a significantly higher level of specificity, and maybe something that is not so easy to see here, but very important, is that using the continual learning model approach, it's much more robust for the future trainings when you change the data distribution. I mean, if you think about it, if you would continue to having the distribution that will mimic the real life thing, meaning that there would be just 1% of the FCDs, at some point, the model will just say, hey, I'll just optimize my function, I will always say there's no FCD, and then I'll achieve like 99% of accuracy because like just this 1% is not so relevant. But the super interesting thing with continual learning here is that we have trained the model in the first stage to very well recognize the FCDs and where they are, and then we're still keeping this knowledge. So it was still there, so we were penalizing the models not to change these weights, and then we are also training it that, hey, right now there is also like different distribution of the data, so work against these false positives. And I think that the way that it would work in the future is that it will still keep the important information about the FCDs, while also later on improving on the false positives. So this approach will bring, like in next iterations, when we train it for 20, 30 more rounds, it would bring much better results on sensitivity. So the doctors that we have worked with, they were also very enthusiastic about it, and they said that it's really useful for the daily clinical practice and the early detection of FCDs. So let's summarize here. So we have learned that the neural networks, they tend to forget old stuff when learning new things, and this phenomenon is called catastrophic forgetting. And the thing that's helping us against this is called continual learning. So it allows the model to keep learning based on the new data without forgetting previous skills. We've also seen that there are different kinds of continual learning methods that work well under different circumstances and for different kinds of problems. We've also seen that there are some niche AI applications beyond writing emails, writing code, or generating next Ghibli-style pictures that really can bring values even though they are not so much used in the headlines of the news. For example, such as using machine learning to help expanding access to epilepsy surgery by improving the diagnosis of drug-resistant focal epilepsy. If you're interested into more details, so we have published 2 scientific publications in epilepsy research. So this is one of the most important journals in the area of epilepsy, where we describe in much more detail the architecture of the neural network, the data sets that we used, as well as the specific functions for the regularization and for the continual learning. But I told you that there will be 3.5 acts here. And if you listen carefully, I told you that there will be no LLMs here, but, well, let's say maybe I lied a little bit. So probably many of you are thinking right now, hey, so it sounds good with this continual learning, especially this part connected with, like, it really takes a lot of resources to compute the big models, especially large language models, for example. So how about using continual learning together with LLMs? Well, this is very intensely researched area right now. So there are lots of things happening here. According to the information that I found on the internet, none of the big providers is currently applying continual learning in any of the models. But there are really a lot of work being published about this. If you're interested about it, I can also afterwards send you some links to some repositories connected with it. But why is that? If you think about how large language models are being trained, they are not just being trained once, right? So there are different steps, like different machine learning trainings being done to get them. And thus, we have also different kind of continual learning to apply them. So we have the continual pre-training, so that the models can learn the new events about the new knowledge that is being published. But we also have the continual instruction tuning, meaning that we can adapt continuously the way, like, how the models should follow our instructions. And then we also have the continual alignment, meaning that the model should also follow the way the human values that we would like to bring to them. And each of the steps can be adapted or continuously trained separately, but unfortunately they also infer between each other, meaning that if you do it for one step, it can also influence a bit the next stages. But nevertheless, it's being, as I said, quite heavily explored. And I think this is, like, really important area that we take in mind. If we ever want to have, like, truly intelligent kind of AI, I do believe that continual learning is going to be on the next wave. Like, the models that should really be able to use what they know about their previous task, use their knowledge, and learn from experience like we do. I think this is going to be one of the most important features and maybe one of the next waves of AI. Maybe not necessarily using large language models. Maybe this is going to be like completely different architecture. But I think this is gonna be like really important and fascinating area of AI. So with that, thank you very much. I hope you enjoyed the whole conference as much as I did. And if you would like to talk a bit more about continual learning or AI in general, then let's stay in touch. So thanks a lot.